the way this book was arranged, there's a lot of overlap on that first chapter with what we're doing. I feel like now we're really doing things more rigorously. Rigor is that thing that you do in mathematics until right before you get rigor mortis, and then it's over. So we're gonna look today at something. Look at the real zeros of polynomials. So we're not gonna be concerned. We're not going to be concerned with complex solutions, complex zeros. And there's a few observations I want you to make about polynomials that are kind of neat. So I'm going to start with an example. Suppose I have a polynomial and it has real roots 2, 3, and negative 4. So we can construct that polynomial pretty easily. P of x is going to be x minus 2 times x minus 3 times x minus 4, or x plus 4. And we're gonna find out what the polynomial looks like in standard form here. So x minus 2 times x minus 3, that's x squared minus 5x plus 6 times x plus 4. I can still almost, it's not FOIL anymore, but I can still do this pretty rapidly here. So x squared times x is x cubed. X squared times 4 is 4x squared. Minus 5x times x is minus 5x squared. Minus 5x times 4 is minus 20x. And 6 times x is x. Did I do something wrong already? Oh, okay. Okay, so we simplify this plus minus x squared minus 14x plus 24. Something I'm sure all of you can do. Now, here's the first observation. It's the easiest one. Well, 24, forget the sign for a second. 24 has to be 2 times 3 times 4. Can you see why that is? Right? I mean, in the process of multiplying this, I multiply minus 2 times minus 3, and I get 6, and then I might multiply it by 4, and I'm going to get 24. Not as clear right now is that since the coefficients of x is always 1, the coefficient of the leading term will be 1. So we got the leading term, and we have the constant. So we know something about them just kind of looking at this. Now here's something. There's something you might want to ponder for a second. Minus 2 plus minus 3 plus 4 is, minus 5 plus 4 is minus 1. Might be a coincidence, but it just so happens that's the coefficient on this term here. It might be a coincidence. We'll have to look into that. So we want to look at this issue a little more directly. So let's do something very abstract here. I want this polar word so bad. So let's say I have some linear terms, and I'm going to name this A0x plus B0, and I'm going to multiply it by A1x plus B1, and I'll have some number of terms here. I'm going to have n terms. N could be a small number or a large number. Well, if we multiply this out, we can immediately figure out a few things without, too much stress. We can see that there's going to be an x to the n here, right? Because there are n of these, so there are n x's. But the coefficient here is going to be A0, A1, A2, all the way to A to n. In other words, the product of the a's. And in between here, there's going to be some other stuff. And at the end, we're going to have a constant term, which is going to be B0, B1, B2, all the way to B to the n. I think that's obvious, but maybe it's not. I'd like to actually, let's do an example here. Let's take A0x plus B0 and multiply it by A1x plus B1. So we're going to have to FOIL that. So we get A0, A1x squared plus A1B0x plus A0B1x plus B1, or I can combine these and I just get A0, A1x squared plus A1B0 plus A0B1 x plus B1. Okay, so the leading coefficient and the constant term are what I expected. Now, if all the a's were 1, this would be the sum of the b's. Remember, I mentioned that this was minus 1. This is just in the case of x squared, second degree. But I'm curious, what's going to happen the next round. When this is, I guess, where the rigor mortis starts to set in here. Let's multiply this times A2 x plus B2. Well, this is a big effort. We're not going to gain that much from it. I mean, we already know that this term is going to be A0, A1, A2, right? X cubed. And we know the constant term is going to be B0, B1, B2. I'm going to cheat and I'm going to show you just what you get here. The second coefficient, A0, A1, B2 plus A1,
B0, A2, B1, plus A1, A2, B0 times x squared, plus, and I'm going to make sure this fits in, A0, B1, B2, plus A1, B0, B2, plus A2, B0, B1 times x. Okay, this is a big mess. I mean, I can deal with this, and I can deal with this. And again, I can notice that if all the a's are 1s, this is just B0, B1, B2, the sum, just like I said here. So this isn't a coincidence. If you look here, you kind of see a pattern growing here. It's not that easy to put a label on it yet, but we're third degree, and this is the sum of 3 items. You see 2 A2s in each of these. You see 1 B, and the indexes are, they all kind of rotate around. Right? We don't have A1, B1. We have A0, A1, B2. This term, this coefficient, you see something similar, except now instead of 2 A's, you have 2 B's. Oh, so here we have 3 A's, 2 A's, 1 A, no A. No B's, 1 B, 2 B, 3 B's. So it's kind of a nice pattern growing there, right? If we went on, we would continue to see that pattern. But that's as far as we're going to push this. In this class, we're as far as we're concerned, these are just the guys. What we're really concerned with is the A's and the B's. So why are we concerned about them? Well, let's assume for a minute that the roots of this equation, of this polynomial, are rational. No square roots, nothing weird. Well, the roots here happen to be negative, what? Negative B0 over A0, negative B1 over A1, negative B2 over A2, and so forth, assuming they're rational. So, if we look at a particular value, if we look at this value, B0, B1, B2, divided by A0, A1, A2, we can say something intelligent now about these rational roots. They're all a factor here. They're all factors. Does everyone see that? Now, when you get a polynomial, you don't see B0, B1, B2, and A0, A1, A2. You just see the coefficient. But you can make this fraction here, and you know that if there are any rational roots to the polynomial, they will be a factor. So that brings us to the rational root theorem. I think I mentioned this before because it came up in the book. Rational theorem. Okay, so all this stuff you've seen now, that's just for your entertainment, for your personal enjoyment and satisfaction. But this is what the point of this is. The rational root theorem says that if we have a polynomial with leading coefficient A and constant term B, that if there are any rational roots to this polynomial, they will be a factor of B over A. Well, that could be useful, or it might not. It depends on the polynomial. Make some here. Let's take an example. A simple example to start. Say our polynomial is x cubed minus 3x plus 2. This is a polynomial that's third degree, so we don't really know we can find the roots. We don't have a straightforward way to do it. But we can at least eliminate the possibility that it has a rational root. So we look at the leading coefficient divided into the constant term. That's 1, it's 2. And we think of what are the factors of 2? Well, certainly 2 is a factor. Remember what happened with the negative signs. The negative signs can get lost, so minus 2 could be a factor. 1, that's always a possibility, and minus 1. So now we just have a short list of possible factors. But what are we going to do with those? Well, I mean, these tell us what the roots might be, right? They also tell us what the factors of this might be. So how can we tell if one of these is a root? Or, you know, if 2 minus x, x minus 2, x minus 2, x plus 2, x minus 1, x plus 1, whether these are factors here. Well, on Monday, we looked at something called the factor theorem, which tells us if I plug one of these roots in here and I get 0, it's a factor. So let's start easy. Let's start with 1. Oh. I think I should have started hard. Made it more difficult. 1 minus 3 plus 2 is 0. So that means 1 is a root, or x minus 1 is a factor. Well, since this is third degree, that's really all we need. I mean, we can check these other numbers. We can check minus 1. So minus 1 plus 3 plus 2, that's not going to be a root. We could go through the list, but we don't really have to at this point. Yes?
Can you go over that one more time with the x minus, or the plugging in the 1?
Say again, go over again the...
Can you just go over, like, plugging in the number?
Oh, well, I'm not sure if this is what you're asking, but what I was saying was p of 1 is 1 cubed minus 3 times 1 plus 2. So that's 1 minus 3 plus 2, or 2 plus 1 is 3, minus 3 is 0. Is that the question? Okay. Yeah, you gotta put the brakes on if I do something too fast and you don't see what I did. Thank you. Okay, so what am I going to do here? I'm going to throw caution to the wind, and I'm going to try and do this using synthetic division. So my coefficients are 1, 0, minus 3, and 2. And I guess my root is 1. So how do I do this now? Bring this down, multiply, I add, multiply, multiply, add 0. Oh, good, worked. Is everybody comfortable with that? Because I'm not. Right? This tells me that x minus 1 divided into x cubed minus 3x plus 2 is, and then I just have to write down the coefficients here, x squared minus x plus x minus 2. Right? Well, as I said, since it was third degree, this is now second degree, and I don't really have a problem with it because I can use the quadratic formula to find the roots here. Right? Whenever I get something down to second degree, you know, there's kind of a quick, easy way. So let's take a look. Negative b would be negative 1 plus or minus the square root of 1 minus 4 times ac, which is minus 8. Plus 8 all over 2. This is 3. This is 9. The square root of 9 is 3. So negative 1 plus or minus 3 over 2. So that's 1 and minus 2. Okay, so those are my other roots. So now I'm prepared to say, okay, I know how to factor this. It's x minus 1. That was my first root. X minus 1 again, okay, and x plus 2. Okay, so to summarize, I can look at my constant factor divided by the coefficient of the leading term. I can look at all the possible factors of that value, looking for rational roots. I can try some. If I find them, I can divide them out, and hopefully I can factor my polynomial that way. Any questions about this? Yes.
Say if you found two other roots, like you just plug them in, you found x minus 1 and x plus 2 for the factors, and you divided out x minus 1 first, and then divided out x plus 2. What would you do with that?
I mean, that's fine. It doesn't matter which way you do it, which order. Is that your question? Would it come out the same? It better. If it doesn't, all of math falls apart. And, you know, society is in ruins, chaos. Evil demons come and take over the earth. It's really about how bad it would be. Or you made a mistake. So you better, that's why you check. Okay, now that we know how to do it, with an easy problem, let's take a look at a hard problem. Harder one that somebody's going to have to sweat over here a little. Let's take a look at polynomial 2x cubed plus x squared minus 13x plus 6. Now, this is much harder, and I led you wrong in the first example. It's not so much 6 divided by 2 as the fraction 6 over 2. We have to look at all possible factors of that. So 6 is 1 times 2 times 3, and 2 is 1 times 2. That's not really what I want to write. What I really want to write is, what are the factors of 6? Well, there's plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. And 2 has factors plus or minus 1, plus or minus 2. A lot of combinations here. We can ignore one set of plus or minuses because, you know, there's only 2 possibilities in the result. It's either plus or it's minus. So what are our possibilities? There's 1 over 1, plus or minus to say so. There's plus or minus 2 over 1. There's plus or minus 3 over 1. Plus or minus 6 over 1. But then we could also have a 2 in the denominator. So there's plus or minus 1 over 2. 2 over 2 is just 1. We did that already. Plus or minus 3 over 2. And 6 over 2 is just 3 again. So 1, 2, 3, 4, 5, 6 times 2 is 12 possibilities. So what we really want to do is we want to get lucky. Let's start easy. Let's try something easy. Let's try 1. So this is 2, plus 1 is 3, plus 6 is 9, minus 13, that's 9. Plus 1 is out. We try minus 1. Minus 1 plus 1, that's 0. That's 13 plus 6, that's out. So that didn't work. Well, you know, get the rest of class, so let's keep going. Let's try 2. 2 cubed is 8, times 2 is 16, plus 4, minus 26 plus 6. 16 plus 6 is 22 plus 26. 0. I got lucky again. So I know that p of 2 is 0, or x minus 2 is a factor. And once again, I can use synthetic division. Starting to like it. All right, so when 2 comes down, 2 times 2 is 4. 1 plus 4 is 5. 2 times 5 is 10. I add minus 3. 2 times minus 3 is minus 6. And of course I get a 0 remainder. And the polynomial I'm left with is 2x squared plus 5x minus 3. So once again, I get lucky, and that'll be easy to solve using the quadratic formula. Now, you might ask me an obvious question. What happens if none of these roots, I have to go through the whole list, none of them are a 0. None of them go to 0. What happens? What does that mean? Well, what it means is that this polynomial doesn't have any rational roots. And a third degree polynomial that doesn't have any rational roots, we don't have to handle that. If I mentioned, there is a formula you can use that will give you the result with radicals. But we won't do that in class. The only thing you can do with it is you can try and find an approximate solution. Yes?
Did you say there could be more than one rational root?
Oh yeah, they could all be rational roots. In the first example, they were. They could all be rational. A subset could be rational. None could be rational. Now, remember, we're just looking at real roots here today. So the polynomial may not have any real roots. Just as a side note, I know I mentioned this. If we have a polynomial where n is odd, then we know we always have one real root. We know that because we know the end behavior. Well, if this is positive, it's going to go up over here, and it's going to go down here. And somewhere along the way, it has to cross the x-axis. So polynomials of odd degree always have one root, guaranteed. Using this rational root theorem is just, you know, it's a little bit of act of desperation. You know, it's not a quadratic we're looking at, so it's more complicated. Maybe it's third degree, fourth degree, fifth degree. But if it happens to have a rational root, we can simplify it. We can find that factor, we can find that root. But there's no guarantee here. All right. I was wrong. We are going to have movies today. I'll get that going. Now, I want to say something about the chapter. I think everyone here is smart enough and mature enough to realize that it never hurts to look at the chapter, the book we're working on. Going to turn on for me. Having technical difficulties here. Oh, what's the problem? Monitor. Okay. Here we go. Okay. Success. As I was saying, it's always a good idea to take a look at the chapter. You shut down your computer because of a problem. So, the book talks about two other strategies that you might use with the rational root theorem. Get to where I want to go. One of these is called the upper and lower bounds theorem. And the idea is you use some technique to find out, well, I can't have any roots greater than this, and I can't have any roots less than this. So therefore, I can eliminate some of these choices. It doesn't add anything more, it just might save you some time. The other thing they have in the book is called Descartes' rule of signs. Now, when you hear the name Descartes, you should always pay attention, because Descartes was a very prominent mathematician. But his rule of signs itself, it's more complicated than anything we're learning today. So I don't want to emphasize either of these. In the future, you will need to know how to factor polynomials, but you won't remember these things, or you won't want to, because, most likely. So anything that has to do with those two, if I accidentally give you a homework problem that has to do with those, please write me an email and ignore it. But there is another technique that can be useful, which is to use a calculator. Either like a TI calculator, or in this case we're going to use Desmos. And let's put in a rather ugly looking polynomial, 4th degree. Okay. You can just barely, everybody see the red line? Okay. We can just barely see what's going on here, so let's back up a little. Okay. It's pretty clear now what's going on. This is 5th degree. No, 4th degree. Yeah, this is 4th degree. 4th degree doesn't have to have any real roots. But we can see right here, it's going to pass through the x-axis. So it's going to have, you can see it has 2 real roots. Now what are they? Well, we're gonna zoom in a second, but you can see it's a little bigger than 1 here, and between 0 and 1 here. With a TI, there's a function. Not a mathematical function, a button. That will, you just tell it, I want to find the 0 near here, and it will do it. Desmos might have that, but I haven't found it yet. But Desmos has another nice feature, because we can just zoom right in here. It's I'll move it towards the center. Okay, narrow it down a little. It's between 1.2 and 1.4. It's close to 1.3. Everybody seeing this? Yeah. You can just. This is, instead of like using math, this is using fingers on a mouse. So to whatever degree Desmos will allow me to. So what have I got here? 1.3025, 6, 7, 7 point something. This is for a real world problem. You're actually trying to find the 0 of some polynomial. You have the function, you don't need an exact number. The exact number probably has a radical in it. We can try and guess what that is, but it doesn't really matter. This is only good to get an approximate value. So, again, with any particular piece of software, you just have to play around with it to see how it works. see if it'll get you your answer. There are other strategies too. This is just a really nice modern one. If you're a computer person, I mean that in a positive way, computer science major, you could write a program. You could write a program that would try and zero in on this. Does anyone have any ideas for an algorithm that you might use? Algorithms. Someone want to tell me what an algorithm is? Aaron, you know what an algorithm is, don't you?
This is simple terms, just a pattern.
God, I can't hear it.
In simple terms, it's just like a pattern.
You heard pattern. So, can everybody else hear him? Because that's what's important. Do some kind of process, some steps, right? What steps could we use to find, with a computer, to find zero? Any thoughts? No? All right, I guess that's what I'm here for. The first thing you have to do, you have some polynomial somewhere, right? And you don't know what it looks like. And somewhere, you know, maybe it crosses the x-axis. The first thing you have to do is find a place where it crosses the x-axis. So how could you do that? Well, you can start, let's say you start at 0, and you find out its value is 0, and then you start moving around, right? What makes this tricky is, you know, maybe the function does something weird, like maybe it goes like this, and you jump from here to here, and what you're looking for is for it to change sign. So maybe you jumped too far, so you can always try using little jumps. But again, the first thing you want to do is you want to find out some place where the function is negative and some place where it's positive. If you remember Wednesday, we talked about the fact that if you have 2 points and the function is negative in one and positive in the other, or the opposite, there has to be a root between them. So once you do that, it's pretty easy. You just say, okay, let's check some other points, right? Let's move along the curve. And then you wait for it to switch signs again. Right? And once it switched signs, then you make your increment a little smaller and you go back in the other direction and wait until it switches signs. So essentially, you keep moving in. You look for an x that's approximately 0. You just kind of get closer and closer. That's what the TI does. I don't know, has anyone used the TI to find a 0 before? And I say, yes, Paul. Have you used that find a 0 function? Okay, so you know one of the things it wants you to do is it wants you to take a guess, right? Because it's not really that good at guessing the first place to start. But if you look on their little graph and you say, oh, I can see it crosses the x-axis, give it a starting point. All right, so that's it. That's it for finding real zeros for using the rational root theorem. You might want to try this. I don't think I'm going to have any homework, but especially if you're a computer science person, but even if you're not, you might want to try either using Desmos, or if you have a Mac, you can use Grapher. Or if you have a TI, definitely get familiar with that. Okay. We're not quite done yet. Okay. So now we're going to open things up a little. We want to look at complex zeros or polynomials. And we're going to start with something that's called the fundamental theorem. Fundamental definition. Do you know what fundamental means? It's okay.
It is such
Good
a-
vocabulary word. Somebody. Ashley, you look like you know what fundamental is.
Like a basic.
Basic. Carlos, could you add anything to that? Like basic structure? Basic structure. How about important? It's something fundamental, something important, right? What's the fundamental reason you're here? Well, that might vary. Get an education, right? In this class, hopefully to learn math. I come from like, you know, a long time ago in the dark ages, and one of the reasons people would say they'd go to college is to meet someone to get married. That doesn't sound like a good reason. Doesn't sound fundamental. But, all right. Okay, so fundamental theorem of algebra. I'm just curious, does anyone here know any other fundamental theorems in math? Fundamental education system. Anyone know what the fundamental theorem of arithmetic is? Anyone know what that is? Anyone heard of this? Well, before I tell you the fundamental theorem of algebra, it's the fundamental theorem of arithmetic. It says if you have a number, let's say 12, and you break it down into its prime factors. What are the prime factors of 12? Now, if somebody doesn't answer this, I'm just, you know, my head's going to explode. What are the prime factors of 12? 3, 2, 1's not a prime. 4 is not a prime. No, those are factors. The prime factors is what. Well, really, there are 2 2's, right? There's 2 2's and 1 3, right? So the fundamental theorem of arithmetic says if you break something down, a number down into its prime factors, that factorization is unique. There's only one way to do it. That's pretty fundamental. I don't know why that's the fundamental theorem. All right. The fundamental theorem of algebra is not really complete. We're gonna complete it, but it's very strange. What the fundamental theorem says is if you have a polynomial it has a root. The book will emphasize it has a root in complex numbers. Could be a real number, could be imaginary. Both of those are complex numbers. But every polynomial has a root. Now, when I hear that, I feel kind of like, so what? Okay. All we've said is it has a root. That means if you have a polynomial, there aren't any polynomials with no roots. But it doesn't feel very satisfying. Let me just write it down. Every polynomial has a root. So, what we really want to know is this theorem, which is a corollary of the fundamental theorem of algebra. Did I ask in this class what a corollary was? Did I get an answer?
No.
What's a corollary? It's a proof that's derived from another theorem. But it's usually like small and easy or pretty obvious. This is actually a very hard theorem to prove, and we're not going to do it. But once we have that every polynomial has a root, then we're kind of golden. Because if p of x has a root, let's call it, we're going to call it C1. That tells me that by the factor theorem that p of x is equal to x minus c times some other polynomial. Remember this from Monday? Well, clearly if this polynomial has degree n, this will have degree n minus 1. So this polynomial, by the fundamental theorem, also has to have a root. Right? We'll call that C2. So then we know that p of x is equal to x minus c1 times x minus c2 times some other polynomial. Let's call it r of x. And we can keep doing this, right, until whatever polynomial we have here is just degree 1. It just has one root, and then we're done. So the corollary, which is called the complete factorization theorem, that's what the book calls it. I've heard it called other things. It just says a polynomial of degree n has n roots. That's the real theorem we want, right? Let me write that down. Polynomial of degree n has n roots. And I'll make the author of the book happy over complex numbers. Well, that's really beautiful, you know? I mean, once you accept this, this becomes obvious. But that's really nice. I mean, if I told you, you know, if I say x to the 7th minus 3 equals 0, you don't have to ponder too hard to know this will have 7 roots. I don't know what they are. I don't know if I can find them, but it will. Some of them may be complex. Some of them might be rational, although we can kind of eliminate rational pretty quickly. Can anyone tell me why I know there are no rational roots to this? Because we learned how to do that today. What are the possible rational roots for this polynomial? You should know this by now. Somebody. What does the rational root theorem tell us? Are you looking it up, Albert? No. What are the possible rational roots of that polynomial? Want to look at 3 over 1. So plus or minus 1 over 1, plus or minus 3 over 1. Well, we can check those out real easily. 1 minus 3, no. Minus 1 minus 3, no. How about 3? That's really way off base. I know right away there's no rational root. I know there's one real root at least. How do I know that? Because odd degree, yes. It's not an odd function, we'll careful, yes. You were thinking the right thing, but you said the wrong thing. I do that every day. All right, that's it for today. I will have a homework assignment up probably tonight that will probably be due Monday.